Okay, now we want to talk about the different layers of the Earth. And so we mentioned so far that the Earth had a solid iron core, it has a liquid outer core, it has a mantle composed of dense rocks, and then it has a crust composed of not so dense rocks. Well, how do we know that? So, the deepest that we've ever drilled inside the Earth is about 12 kilometers. So, that's the deepest wells that we've ever dug have gone down that deep. But the radius of the Earth is something like 6,400 kilometers. And yet, we think that we know what is inside the Earth. So, how do we know what's inside the Earth if we can't physically get to it? Well, a lot of it is based on theory. So here's some ideas that we use to tell us what's inside the Earth. So the first is, what is the Earth composed of? The overall composition of the Earth would be similar to the overall composition of an asteroid. And so we have found sample asteroids on Earth, and we have analyzed their chemical composition. So we think that the Earth basically has the same composition as an asteroid because that's where the Earth came from, is the collisions of asteroids. Okay, then the next thing is, what about the mass of the Earth? How do we know what the mass of the Earth is? So we know what the density of the Earth is because we know what the density of an asteroid is. And we know that density rho is equal to mass divided by volume. So if we want to know what the mass is, we need to know what the volume of the Earth is. And even the ancient Greeks had a pretty good idea for what the size of the Earth was and what the volume of the Earth was. So based on that, we can calculate the overall mass of the Earth. Okay, then the next thing is, how do we know what the pressures are like inside the Earth? And so just like we know what the pressure is like at the surface of the Earth because it's caused by the weight of the atmosphere pushing down on top of us, then we can calculate what would be the pressure inside the Earth based on the weight of the rocks that are on top of you as you go deeper and deeper inside the Earth. So the pressures can be calculated. Okay, then we can also estimate what the temperatures are like inside the Earth because we've got a pretty good idea as the what was the initial temperature of the Earth, and we know the additional heat that's produced by radioactivity, and so that gives us a good idea for what the temperature is like inside. And then we leave it up to the chemists. So now that we know what the Earth is made of, and we know what the pressures are like, and we know what the temperatures are like, it's just a matter of chemistry. So in chemistry, if you know what chemicals you're starting with, and if you know what pressures they're under, and you know what temperatures they're at, you can predict what they're going to turn into. And similarly, we can predict at different levels inside the Earth what the kinds of rocks would be like as we go deeper and deeper inside the Earth. So let's take a look then of what does the inside of the Earth. Now we want to verify it. So we've made our predictions as to the different layers inside the Earth. How do we actually measure it? And we do this by using seismic waves, so that every time that there's an earthquake, it's going to send through the Earth earthquake waves. Later in the course, in the video series, we're going to talk about the difference in different kinds of earthquake waves. So they're called S and P waves. And one of the key things, though, is that a P wave can go through a liquid, but an S wave cannot. And so every time that there's an earthquake on the surface of the Earth, it's going to generate these S and P waves. And we cover the surface of the Earth with seismic detectors so that we can measure these earthquakes as waves as they travel through the Earth. And what we noticed was that there were certain areas inside the Earth that would not transmit those S waves. So that must mean that certain parts of the Earth are liquid in their composition. And so based on the seismic waves, we were able to map the inside of the Earth. And we'll look at this in more detail in another lesson in the future. So what are the Earth's layers then? Okay, now if you had lived back in the 1950s, things would have been much nicer in your geology class, because in your geology class they knew that the Earth had a core composed of iron and nickel, and they knew that it had a mantle composed of dense rocks, and that it had a crust composed of not so dense rocks. That was basically it. All right, so things were much simpler back then. So that was the layers of the Earth based on composition. What was the Earth composed of? Okay, but then along comes the seismic wave stuff. Okay, and then we started to find that the Earth had much more structure to it. So then, based on the state of the material, so you have gas, plasma, liquids, and solids. So those are the four states of matter. Well, inside the Earth, you don't have gases. So you would have liquids and solids. So according to the state of the material inside the Earth has a solid iron and nickel core, and then it has a liquid iron and nickel core. So the outer core is liquid iron and nickel, the inner core is solid. And we said that it's the outer liquid iron nickel core of the Earth that generates the magnetic field of the Earth. So that's why it's important. Okay, then on top of that is an area called the mesosphere. And now if you look at that picture, you'll notice that the mesosphere is just about the same as the mantle. Notice that the mantle is bigger. So the mesosphere is part of the mantle, but you would not want to say that the mantle is part of the mesosphere, because the mantle is larger. So the mesosphere is the middle part of the Earth. This is going to be the part of the Earth that is convecting. So we haven't talked about convection much, but when you boil water, water rises to the surface and then it goes back down. So this is called convection when that happens. You also have convection in the atmosphere, so that helps to make clouds. Well, convection inside the mesosphere of the Earth is what is going to be causing plate tectonics. And we'll talk about plate tectonics in a future lesson. So plate tectonics is the movement of the plates that make up the surface of the Earth. And when they bump into each other, they can make mountains. When they pull apart, they can make ocean basins. They can slide past each other. So we'll talk about that in a future lesson. But the origin of plate tectonics is in the movement of material in the mesosphere. Now the mesosphere is solid, so that if you wouldn't want to go into the mesosphere because it's so incredibly hot. But if you were to feel something in the mesosphere, it would be solid. But yet it can move like a liquid. So in the mesosphere you have convection, and in a future lesson we're going to find out why can it move if it's a solid in the mesosphere. Now on top of the mesosphere is going to be an area that is not quite solid and it's not quite liquid. So it has the consistency of plastic. It can flow. And so this is going to be called the asthenosphere. It's a very thin layer on top of the mesosphere, and it's slippery. It can move. And on top of the asthenosphere is going to be the lithosphere. So the lithosphere is going to be composed of solid rock. It kind of corresponds to the crust of the Earth. But as you can see in that picture there, the lithosphere is a little bit thicker than what the crust is of the Earth. But in your head, you can say lithosphere, crust as being the same thing. But the lithosphere is going to be solid, and it is broken up into plates. And then those plates are going to slide around on top of the asthenosphere, and then that is going to be plate tectonics. So as these lithospheric plates move around, they're going to bump into each other, they're going to be pulled away from each other, they're going to slide past each other, and that's going to be what plate tectonics is all about. Okay, so that's it. So let's take one more break, and when we come back, let's do a quiz over what you've learned.